Okay, so I'm back now with a three-phase circuit for us to solve. This is a pretty simple one. It's a wye-wye as indicated by each source, and load is connected to the neutral. I have a nice neutral wire. And I'm just saying, find the power absorbed by the load. I gave the impedance of the line, impedance of the load, and the voltages of each of the sources. This problem I just came up off the top of my head like 2 minutes ago, so I don't actually know the solution. Whatever we get is what we'll get. So, with this three-phase problem, now I'm not going to solve it using any equations or anything. I'm just going to go from superposition to kind of show, like, if you don't know what's going on, this method should work. So if I go superposition, I should be able to look at one of the sources, and because each of the three sources are just offset by the 120 degrees, and the whole circuit is equal, it's balanced, that if I solve the power for one of the sources, the power for the other sources should all be the same. So then the total power would be the power of the one branch multiplied by 3. But let's just go superposition for branch 1. So VAN. I'll redraw the circuit with only that top source active. The line. So in the other sources, they will be shorted because they're voltage sources. Draw the other ones there. I still have my neutral going around there. Right, so I shorted the two other sources. I'm only looking at the top one now. Well, in this circuit, if we notice, these two lower branches, they're shorted together because we got rid of the voltage source. So this part is shorted to here. No current can possibly flow through here, so I can just get rid of them, right? So now, when I redraw the circuit again, I end up with VAN, the line impedance, the load impedance, and my neutral wire. So the actual power absorbed by the load will be the power absorbed by ZY. Now I'm going to use it from the S, complex power S equals P plus JQ, where the P is what I want. So this will equal VI conjugate. I can use the rule V equals IZ, where Z is the impedance, because I can find the total current, because I can get the total impedance. The total current will be I, then I equals VAN divided by Z line plus ZY. So actually I can take the V equals IZ, and I want to replace the V here. So if I plug it in directly, move that there, put that there, P plus JQ is equal to IZ times I conjugate. And this I can solve because my I is equal to 120 angle 0 degrees divided by Z line, 4 plus 4J, plus ZY, plus 10 minus 2J. So this equals, I have to grab my calculator. So I have my calculator. I'll do 120 angle 0 divided by 4 plus 4j plus 10 minus 2j. And this is 8.4 minus 1.2j. It's in rectangular, but the numbers are clean, so I'll just keep it that way for now. So that's I. P plus jq will equal to 8.4 minus 1.2j times z of the load, so zy, 10 minus 2j times I conjugate, so 8.4 plus 1.2j. Now I'm going to put this all into my calculator. 10 minus 2j, 8.4 plus 1.2j. Double check I just entered that correctly. This is equal to 720 minus 144j. From analysis, this will be my P, and that's Q. But this is actually the P just for the first branch. There's two other branches, so there's 3 branches total. So P load equals, I call it 3 just P. So 3 times 720 is equal to 2160, its power, so it's in watts. And why is it 3? Well, there's 3 branches, they're all balanced, so from superposition I found the first one, and then the other 2 will just be the same power over the whole, his equation works for over the whole period. End result, 2160. And that's how you solve a really simple 3-phase circuit, but it should get you started. Okay, thank you and have a good one.